So welcome, I'm Baylor Jones.
I'm Justin Eldridge.
And today we'll be going over the internship we had earlier last summer, which tested the viability of moss stems exposed to near space conditions, which went up in a weather balloon that we created a payload for to test moss survivability.
Sweet. Mosses are essential for terraforming because they can inhabit barren, rocky landscapes in the absence of other vegetation. They can survive long periods without water by protecting their cells during dehydration or repairing them on revival. They can reproduce sexually through spores or asexually by fragmenting. Sexual reproduction is favored for preserving genetic diversity, but has stringent moisture, pH, and temperature requirements that may prove hard to find. Asexual fragmenting, however, is a hardier process with fewer requirements. The viability of sexual reproduction has been established for mosses exposed to simulated long-term low Earth orbit conditions, while the viability of asexual reproduction has not yet been established.
Here we'll examine the viability of moss leaf cells exposed to the upper stratospheric conditions and demonstrate the feasibility of low altitude dispersal. We'll cover the design of our payload and our experiment and review the testing regimen before flight, and then relay the results on the ground testing and as well as the launch testing that we did.
Payload design.
So this is our payload design. On the right here, you'll see the schematic or wiring diagram of our payload, which includes the Arduino Mega in the middle. And then we have a breakout sensor, which measured the internal cabin environment, which included the temperature, humidity, and pressure of the cabin. And then we had a GPS module so that we could track our flight. And then for the dispersal system, we had a stepper motor and a servo motor, which opened the bay door during flight to test the dispersal of our moss. Unfortunately, we weren't actually able to drop moss from the payload, but this was just for testing purposes. And then we also had a UV sensor for one of our testing environments, and then an SD card reader that read all of the data from the instruments in our payload. And then we also had an outside temperature sensor that was attached to the outside of the payload to give us the environment as it went up into the stratosphere. The payload, this is the payload structure on the right here. You can see the black kind of truss structure that was made from PETG filament that was 3D printed. PETG was chosen for its resilience to warping due to rapid temperature swings. And then just on the outside of that, it's surrounded by 2 layers of HVAC insulation with aluminum tape used to seal the edges. And then for the UV test or environment, we had 2 panes of quartz UV glass. And then on the inside of the structure, which you can't actually see in this image, were 2 clear plates of plastic that were laser printed, which we mounted all of our electronics to.
For our testing environments, we needed a compartment that could expose samples to radiation while protecting them from extreme temperatures. We used a piece of quartz glass attached to the lid of the payload and a 3D printed container to allow UV light to bathe the samples. The container was attached to the lid in such a way that it could still benefit from the heating system in the payload's interior. We also needed a compartment that could expose the moss to the full brunt of near space. This consisted of a recessed hole in the insulation that was covered with ultrafine steel mesh. This allowed us to contain the samples without providing them any protection. And finally, we needed a compartment that would afford the samples maximum protection. So we used a plastic container to hold the samples in the payload's interior, where the heating system and insulation would protect them from extreme temperatures and the increased radiation. Right, for our experimental design, our species selection, drought-tolerant mosses from water-scarce environments outperform their cousins when flash frozen in liquid nitrogen, and are thus strong candidates for surviving a journey through near space. After consulting with bryologist Stacy Anderson and Dr. Brent Mishler, we selected the species Ceratodon purpurus, Rhytidium rugosum, and Centrichia ruralis for testing. Ceratodon purpurus was chosen as it can change its leaf pigments in response to UV radiation. Our rugosum was picked because it reproduces almost exclusively by fragmenting, and S. ruralis was picked because it can survive rapid dehydration. The size of S. ruralis's leaf cells prevented us from imaging its leaves in a timely manner, so this species was excluded from the results. Dissection, imaging, and sampling. Following our testing, 30 leaves were dissected from their parent stems and imaged using a compound microscope with camera. These images were then annotated with the leaf's length, and then the transect lines were placed randomly along the length of the leaf. The damage incurred by the leaf was determined by counting the number of dead cells along each transect line. The number of dead cells divided by the length of the line gave us a way to quantify leaf damage. We created a box plot to show the distribution of damage and also plotted the number of dead cells along the length of the leaf to get a spatial sense. A positive slope would indicate that the base of the leaf was more heavily damaged, while a negative slope would indicate that the tip was more heavily damaged.
Our 3 moss species were collected here in Colorado. 2 of the species that you saw 2 slides previously were collected up in the Poudre Canyon, actually, while I was rock climbing. And then conveniently, Justin lives up near Red Feather Lakes, and he was able to collect the last species. And all 3 of those species we were able to identify with the New Mexico State University's Flora Archives. And that's where we were able to identify each of the species. So to test the durability of our payload, we had to do a couple of tests. The first being the stair test, where it was thrown down a flight of stairs several times to test the structural integrity of the payload. The requirements for this included a fully finished structure of the payload, as well as weights in the placements of electronic components to simulate the flight conditions. And the purpose of this testing was to test the quartz glass durability, which is on the outside of the payload, and then also just the general durability of the payload. It was important that the durability was strong, that way the mosses wouldn't be flying out of the payload during flight. The next test we did was the drop test, where we dropped the payload, as you can see in the image, fairly small there, from the top of the CSU powerhouse balcony, which was about 25 feet. The testing requirements was the same as the stair test, which included a structurally complete payload and weights in the place of electronic components. Lastly was the payload cold testing. Since it gets really cold up in the stratosphere, we had to ensure that the payload could stay warm on the internal cabin to keep the electronics and the moss warm during flight. The requirements for this was a fully insulated payload, and then an integrated heating system, which we had 3 heaters with a temperature sensor on the inside of the cabin to let us know when we needed to turn those heaters on to keep the cabin warm. And then we also had to have a working bay door to disperse the moss, and which we also tested during this experiment.
And then we also conducted some specimen tests. This is the old version of the PowerPoint, and that's why things are not in the right order anymore.
That's all right.
Sorry. Anywho, to simulate the low temperatures of near space, the payload was held, or the specimens were held in a cooler with dry ice for 30 minutes at a temperature of -30°C. And then to simulate the low pressure found in the stratosphere, we also placed samples in a vacuum chamber for 30 minutes and brought it down to a pressure of 0.193 torr. And then finally, to simulate the increased radiation found in the upper atmosphere, the samples were held at 15 centimeters away from a 70-watt UV lamp for 180 minutes. results.
So for the structural test, which included the stair test and the drop test, the stair test didn't cause much damage to the structure in general. It did bend the corners of the insulation, but it was deemed sufficient for the launch. And then we also did a drop test, and the results for that were broken supports, which you can see on the left image, as well as the center flight tube was pressed through the structure a little bit on the right. Since all of the specimen compartments seemed to be okay during these tests, we deemed that the structure was good enough for launch. During the cold test, we tested for 3 hours. I don't know why none of the words are showing up on this slide.
I think I have to refresh the page. Sorry, give me just a second.
Okay. Anyways, during this, I'll just talk about the cold test while he's refreshing it. So we put the payload in a cooler with a bunch of dry ice, where we measured the temperature over the course of 3 hours, just to make sure that the heating system kept the internal cabin warm. And then we also opened the bay door at the end of that 3 hours, just to prove that the door would work after being exposed to the extremely cold temperatures. And then on the left here, now you can actually see the plots. You can see the internal cabin temperature oscillate back and forth as the heaters are turned on and off to maintain a cabin temperature right for flight. So on launch day, we went to Genoa, Colorado, where we slept the night in a hotel, and then we woke up early the next morning to launch around 7. Right before launch, we had to put all of the MOS in their internal testing environments, which included the UV environment, the internal cabin environment, and then also the completely exposed environment, which was glued with a mesh on the outside of the payload. The final weigh-in of the payload was 976 grams, and the payload was sealed and systems were turned on to measure during flight. This is some of the flight data that we recorded. On the right, you can see that the minimum internal temperature actually got down to -4 degrees Celsius. This was due to an error in the code for the bay door opening. For one of the tests, we had Justin drive up to his house, and with the altimeter, the payload would open the door on his drive home. And I forgot to change one of the greater than less than signs back to the correct facing direction. So the actuation happened on ascent, which resulted in colder cabin temperatures than desired. On this next one here, you can see most prominently the UV test, which was the UV sensor up near the quartz glass that measured how much radiation exposure the MOS was seeing during the flight. You can see on the left, during the max altitude of the flight, you can see it peak, and it drops repeatedly because the UV sensor doesn't always get a perfect reading of the radiation. But you can see the general at the peaks of the readings, how much radiation the payload was receiving.
All right, as you can see in the left graph, in the vacuum test, UV test, and cold test, Ceratodon purpureus showed similar levels of damage relative to the control, which is on the far right. And then for flight, the radiation exposure environment and complete exposure environment were also comparable with the control samples. However, you can see the much higher levels of damage that C. purpureus sustained in the protected exposure compartment. And then in the graph on the right for Rhytidium rugosum, you can see that the vacuum test, UV test, and cold test all showed similar levels of damage relative to the control. And then in flight, the radiation exposure environment and the complete exposure environment showed slightly elevated, but nonetheless comparable values to the control. And then as with C. purpureus, our rugosum showed significantly increased levels of damage in the protected exposure compartment. A sharp spike in humidity was observed in that compartment during flight. Discussion of error.
So one of the prominent sources of error were the sensors that we used. Most of the sensors were generally fairly cheap since they were built to go with Arduino, but they sufficed for our testing of the payload. As well as the bay door opening a little too early, that caused the temperature of the different species all to be approximately the same. The internal cabin was only slightly warmer because the heaters just couldn't keep up with the cold air flowing in through the bottom here.
Leaf selection may have been a source of error for us. Dead leaves are brittle and tear easily, so they were much harder to dissect. So that means that healthy leaves may have been selected disproportionately. Our stem preparation may have caused some error. Ground testing samples were prepared shortly after the clumps were collected, while flight samples were prepared shortly before launch. Our cell counting method was flawed for ground testing. In ground testing, each experimenter counted all the leaves in a given environment, leaving room for individual bias. So for flight testing, each experimenter was responsible for counting 1/3 of the leaves from each environment. And finally, since there were no replications in this experiment and the samples were not randomly distributed through the testing environments, the presence of confounding variables cannot be ruled out.
So in conclusion, the payload was found to be an overall success. We received a bunch of data throughout the whole flight, as well as the long period it took us to recover the payload. And the payload did come down with an open door, which was intended. It just was noticed during flight that the door opened sooner than expected.
And the data we collected suggests that both R. rugosum and C. purpuris can survive and revive after enduring near space conditions. The higher levels of damage observed in the protected exposure environment may be related to that humidity spike in that compartment. And finally, our data suggests that the short-term UV radiation is likely unimportant. Thank you. All right, that's it. We are good.
Great, super fascinating. What a thorough and interesting project. That's super cool. I know you said, Baylor, you have to head out shortly, but are there any questions anyone has? Or I guess you don't mind taking questions, I'm assuming.
No.
Yeah, I don't mind a couple
if you have to go, Baylor, I can do my best.
I'm pretty quick at biking, so I think I could make it back if anybody has any quick questions.
Well, I was curious how long, and it probably was in your grasp, but how long was the balloon up? Like how long was your, was that up actually in those conditions?
I think it was approximately 3 hours. That was total flight though. So
I think it
in
was
the
about an hour and a
condition,
half up.
what's that?
I think it was like an hour and a half to get to the maximum height, I think.
Yeah, so it took about half the time to get up to the max height, and then once when it hit the max height, the balloon popped and then the whole payload fell down. So that they didn't really experience the extreme conditions for the whole 3 hours. It was just probably around like the 30 minutes of the peak altitude, which you can see in the center here of the slide.
I have a question.
Yes.
I'd really like to know what you both found most valuable about the whole process.
For me, it was kind of like just learning personal work things, like learning like when you have a question or you don't know what question to ask, finding someone who knows what question to ask. And then once you know what question, finding someone who can answer your question. And persistence is key. Stacy knows I tried to secure laboratory equipment from CSU for like 3 or 4 straight weeks without getting responses. So she finally just set up a garage lab for us and let us use her house, which was very wonderful.
Special thanks to you, Stacy, for being so helpful throughout the project. You were a great help the whole time. So
yeah, I had fun too.
I'm glad.
Good.
Were there
So
any?
when do you give your symposium or present this at your symposium?
Tomorrow?
Yep.
Okay.
Tomorrow at sometime in the morning,
Yeah.
All right.
very
Good
far
luck.
away from home.
Yeah. I wish you well. I'd be eager to hear about it, how it goes after you get back.
Yeah, we'll have to
Certainly.
let you know.
Where will you be
Alright.
presenting it?
I'm sorry.
Sorry.
Where will you be presenting?
Like at like what institution or it's the Colorado Space Grant Consortium. It's part, I guess, related to NASA, and so they do like 3 rounds of this internship a year: fall, summer, and spring. And then April of every year, everyone comes back together and presents on their payloads and experiments. Did that answer your question?
Yeah, yeah, interesting. That sounds fascinating. Well, cool. Well, any other questions from the group for Justin and Baylor? Comments?
How hard was it to locate the payload once it fell to find it?
Oh, that's a funny story.
Yeah, so we got brief glimpses of it as it was falling down. For the most part, though, the NASA guys had a GPS module attached to their payload, and we were able to track the whole flight string from there because there were several payloads on the flight string as
Yeah,
well.
so they actually
just
have
ours.
they've got 2 GPS modules on the flight string, one at the top and one at the bottom. And one of the flight strings on ascent, the last person let it go incorrectly. So the GPS module smashed on the ground. And so the bottom one died before it got anywhere. And then at the top, when the balloon popped, the bottom one, when it kind of whips around, the bottom one came up and smashed the top one. So then they lost both GPSs, and they had to, they had all of us just standing there, craning our necks for like an hour until one of us saw it. And then we were all responsible for keeping it in sight. And they have a RF or radio generator frequency, whatever. So they have 2 antennas on the top of the chase vehicle, and it takes the difference in time for the signal to get to the antenna. So even if the GPSs go out, they know which direction it is. But once it gets too close to the ground, that stops working. So they really had to have everyone looking for it. And then even like for us, locating it was not very hard. Getting it was very hard. It landed on private property, and we weren't quite sure whose property. So we went and talked to a homeowner, and he said, "Oh yeah, great, we'll help you out. We'll drive out there." And then found out it wasn't on his property, but his neighbor's. And he was feuding with that particular neighbor. So that neighbor would not let us in. And they were negotiating for about 3.5 hours before she finally allowed one guy to go onto her property to get it back. So yeah, it was not hard for us to find ours, but it was difficult for others to find theirs, and very difficult for us to get it.
Something you can't really plan for.
Yep.
We don't know whose property it was going to land on, so.
Any other questions?
I have a final herbarium related question. So since we're talking about herbarium specimens, and I saw your packet with from your moss collections, will you be depositing those in an herbarium, or do you have plans for the specimens themselves?
I've got them
Do we
still in
even have any
storage.
of the
I gave
specimens?
Stacy the stems that actually went up. But the parent clumps, I should put it in an herbarium. That would be nice. I should look
You
into
still
that.
have them?
I
Justin?
do, yes. I found
Awesome.
them in the box.
And I have to look to see, I can't remember, you gave me the ones that actually went up? Or-
Yeah.
I believe I gave you the ones that were
Okay.
actually in the payload.
I will check. I have a lot of moss packets around.
Yeah. All right, I can't find it. Whatever.
That
But
would be
yeah, I'm
pretty
sure Stacy could
easy
help
to
me put it in
document
the
that.
Barry.
Yeah, that would be good for documentation to have it. Yeah.
Tie it to that project for sure,
Mm.
yeah.
Mhm.
I'd stay if I could, but I better get to that meeting. So it's nice meeting you all. And I
Yeah,
appreciate
thank you
letting
so
you guys.
much. Thank you so much and good luck tomorrow.
Thank you. Alrighty. Bye-bye.
Bye, Baylor.
All right.
All righty. Any other final questions before we get to our activities today?
All right. Doesn't seem like it.
If not, I will say thank you again so much, Justin. Yeah, thanks so much for sharing your project. It was great to hear about. And yeah, hopefully we'll